So I would like to tell you about some work I've been doing with Andrzej Rostworowski on anti-de Sitter spacetimes over the past few years. I must confess that I feel somewhat uneasy here speaking at strings because I am a complete outsider in the string world. And my motivation to work on ADS comes from classical general relativity, not ADS CFT. But anyway, the plan of this talk is to start by reviewing work we did some 3 years ago on instability of anti-de Sitter under scalar perturbations. And then I move on to the main subject of this talk, which is instability under gravitational perturbations. Okay, so as you all know, anti-de Sitter spacetime is a maximally symmetric solution of the vacuum Einstein equation with negative cosmological constant, and in dimensionless coordinates t, x, and omega, the matrix, the ADS matrix, takes this form from which you see that it is conformal to half of the Einstein cylinder, which is the metric in the brackets, half because the coordinate x ranges only over a hemisphere from 0 to pi half, and at the equator of this hemisphere we have a conformal boundary. And the equator cross time is a time-like special and null infinity of anti-de Sitter spacetime. ADS has peculiar causal properties. Some of them are listed here. First of all, null geodesics get to infinity in finite time, even though the distance from any point in the bulk to the boundary is infinite. So this space is effectively compact, like a box. Secondly, because this boundary is time-like, ADS is not globally hyperbolic, which means that if you want to study evolution of fields, it's not enough to impose initial data on some constant time slice, but you need to prescribe boundary conditions as well. Now, of course, besides ADS, pure ADS, we will be interested in asymptotically ADS spacetimes, which are defined as spacetimes which have the same conformal boundary, but they might be very different from pure ADS in the bulk. The canonical example being ADS black holes, like Kerr ADS. Okay, so ADS is important because it is the ground state among asymptotically ADS spacetimes, much as Minkowski is the ground states among asymptotically flat spacetimes. Now, for any equilibrium solution, and ground state in particular, the key question is whether this solution is stable, which means whether small perturbations at some initial moment of time remain small for all future times. Minkowski spacetime is known to be stable. Actually, it was proved to be asymptotically stable here in Princeton more than 20 years ago by Christodoulou and Kleinemann. Now, asymptotic stability means that perturbations not only remain small, but actually they decay to zero. And this is what they proved in any compact region of space. Now, the mechanism of asymptotic stability of Minkowski spacetime is dissipation of energy by dispersion. So even though energy is conserved, it is dispersed from any compact region of space by radiation, which escapes to infinity. Now, this mechanism of stability of Minkowski is absent in asymptotically ADS spacetimes, at least for no-flux boundary conditions at infinity, which acts as a mirror. So for this reason, the problem of stability of ADS is much more challenging than the corresponding problem for Minkowski, because perturbations which propagate outwards bounce back at the boundary, and then this leads to some complicated nonlinear wave interactions. So it's no wonder that this problem is open. What is slightly surprising is that this problem has not been really explored quite recently. Here I listed two exceptions I know. One is the proof of local well-posedness of the initial boundary value problem for vacuum Einstein equations with negative cosmological constant in 4 dimensions by Helmut Friedrich. And there is also a paper by Michael Anderson in which he proved that the only asymptotically ADS spacetime which tends to ADS as time goes to infinity is ADS itself. This is another way of saying that asymptotic stability is precluded for ADS. Now, the problem of stability of ADS is very hard, so it's obviously out of reach of current mathematical methods. So it seems reasonable to start with some simplifying assumptions like spherical symmetry. But as you know, in spherical symmetry, vacuum Einstein equations have no dynamical degrees of freedom, so we need to add matter to generate non-trivial dynamics. Well, in GR community, a popular meta model is a massless scalar field. The studies of self-gravitating massless scalar field in the past have led to some important insights concerning, for example, cosmic censorship hypothesis. So, a few years ago, Andrzej Rostorowski and I set out to study this self-gravitating massless scalar field with negative cosmological constant. And here is a conjecture which is a result of our studies, both analytical but formal, like nonlinear perturbation theory, and mainly numerical simulations. So we conjectured that no matter how small is a perturbation, it leads to instability and eventually black hole forms. And this happens throughout my talk, D is the number of little d is the number of special dimensions. So this is true in 4 and higher dimensions. But the heuristic picture behind this conjecture is that the spectrum of linear perturbations of ADS is fully resonant, and this leads to nonlinear interactions between harmonics which transfer energy from low to high frequencies, or equivalently, it transfer energy to finer and finer special scales. And this turbulent cascade is eventually cut off by the formation of a horizon, which is like strongly turbulent instability. Now, I would like to make 2 remarks concerning this conjecture. First of all, the conjecture does not say that instability happens for all perturbations. On the contrary, it is known that there are perturbations for which this resonant transfer of energy is not active. In particular, there is very good numerical and analytic evidence that there are time-periodic stable solutions. This is work by my collaborators, Maliborski and Rostworowski. Now, because of this fact that some solutions lead to instability but some don't, Well, the picture of the phase space in this model is quite complicated. So we believe that there is like a turbulent ocean, and on these are islands of stability. And it's not clear how large are these islands. So, but this means that any attempt to prove this conjecture must take this into account, and this, the proof would be very hard because this conjecture must be qualified by some kind of genericity condition. And the second remark is that this conjecture is restricted to 3+1 and higher dimensions because in 2+1 dimensions, there is a mass gap between ADS and the lightest black hole solution. So we know that small perturbations of ADS in 2+1 dimensions cannot form black hole. We know this a priori. This is a manifestation of the fact that 3 dimensions is a critical dimension for Einstein equations. Nevertheless, the turbulent cascade is present in 2+1 dimension, very much the same as in higher dimensions, except that now it can go forever. We studied this problem with a student of mine, Joanna Jomuzna, and we found that so-called radius of analyticity of solutions shrinks to 0 as time goes to infinity. This is usually referred to as weakly turbulent instability, and this is reminiscent of behavior of solutions to incompressible Euler equations in 2 special dimensions. Okay, so these studies raise a natural question. Well, to what extent the features of this instability, which we found for a spherical scalar field, are model dependent, and which ones hold in general? So there are at least 2 approaches to study this question. Well, one is to look at other matter models. For example, Young-Mills is particularly interesting because it has very nice conformal properties in 4 dimensions, and it would allow to study the role of different boundary conditions at infinity rather than Dirichlet conditions. However, in this talk, I would like to tell you about a different possibility, about a vacuum solution, so which is clearly the cleanest case. Now, unfortunately, there are computational limitations for long-time simulations. And at the moment, we are not able to do long-time numerical simulations outside 1+1 dimensions. But there is a way around this, and this is what I would like to tell you about. Namely, one can bypass Birkhoff's theorem at the expense of going to higher dimensions, or more precisely higher odd dimensions. And I thought that what for me is an expense, for you might be a profit, because 5 dimensions is the right dimension, as I understand, from the point of view of ADS CFT. So that's why I chose this subject. Okay, so let me tell you how you can bypass Birkhoff. I will talk about 5 dimensions, but the same is true. Well, actually, it's even more interesting in higher odd space-time dimensions. So the point is that if you, usually when you think of a sphere, you imagine a round metric. But you can endow a sphere with other metrics. And for example, on S3, the following metric is homogeneous. And these sigmas 1, 2, 3 are left invariant 1 forms of SU2, written here in Euler angles. Now, if these 3 parameters, deformation parameters, B, C, and D, are equal, then the metric is round, and it has a SO4 symmetry. But if they are different, this metric is homogeneous but anisotropic, and it has only SU2 symmetry. and it's usually called squashed three-sphere. Now, this metric might be familiar, for example, from the mechanics of rigid bodies as a kinetic energy of a top, or from cosmology as it appears in Bianchi-9 model. And some time ago, together with Chmay and Schmidt, we proposed to use this metric as an angular part of five-dimensional metric. And somehow, without imagination, we called it cohomogeneity 2 triaxial Bianchi-9 ansatz. And here it is. So we used some coordinate freedom in the two-space orthogonal to the orbit of SU2 group to normalize the volume of the three spheres. That's why only two parameters appear here, because by scaling, this parameter can. And these functions, there are four functions, A, delta, B, and C, and they are functions of T and R. And I will restrict here to a special case when these two parameters B and C are equal, so there is an extra U1 symmetry. This is called biaxial case. Okay. Now, so this was in asymptotically flat situation. We actually studied different phenomena using this ansatz, but the same idea works for ADS. So here is this ansatz again, but now specialized to ADS. So it's the same metric as before, well, the same coordinates. This is the conformal factor. Well, when A is 1, delta is 0, and B is 0, this is ADS metric. So we take this ansatz, insert it into vacuum Einstein equations with negative cosmological constant in 5 dimensions, and we get this system of partial differential equations. So the details of this system are not important, but the structure is the same as for the Einstein scalar field case. Namely, there is one nonlinear or quasi-linear wave equation for the deformation parameter B, and there are two constraint equations for the remaining metric functions A and delta. So A equal 1, delta equals 0, and B equals 0 is a trivial solution of these equations, and this is pure ADS. So what we did, we solved the Cauchy problem, or rather initial boundary value problem for this system for smooth initial data which are small perturbations of ADS. Now, at the boundary, this is the behavior of the fields. And as in the scalar field case, there is no freedom in choosing the boundary behavior. So these are so-called Dirichlet boundary conditions, as long as you want your solutions to be smooth. Okay, so before I present numerical result, I need to tell you about spectral properties. So, which means what happens if you linearize these equations around ADS. So you get a simple Sturm-Liouville eigenvalue problem with this nice operator, which is essentially self-adjoint. The fact that it's essentially self-adjoint means that there is no freedom in choosing boundary conditions. This problem can be solved explicitly. Here are the eigenvalues, the eigenfunctions, and the eigenvalues are odd, well, the eigenfrequencies, I should say, are even integers starting from 6, 8, 10, and so on, which means that the spectrum is, using the terminology of PDEs, is fully resonant. So it's very easy to construct resonant interactions. Now, having this basis of eigenfunctions, we can decompose solution at any instant of time into the generalized Fourier series. And we can also write a linearized energy, which is here, and rewrite it in a Fourier basis. So this EK is energy in the individual mode. Okay, so now I'll show you some results. So this plot shows the second derivative of the deformation parameter b at the center, or the square of this quantity, which is related by this simple linear relationship to the Kretschmann scalar for 3 different small amplitudes. And this is for some Gaussian perturbations, and epsilon is an amplitude of this Gaussian perturbation. And you see that all these perturbations grow very quickly. Actually, they grow exponentially. This is a linear log scale. And eventually, all these solutions form black holes. And of course, solution with the smallest amplitude, it takes longer. Now, if you rescale these 3 curves in a suitable way, they coincide. And this is what is shown. So this is the same plot as before, except that this is now a slow time, epsilon squared time t, and this Kretschmann scalar is divided by epsilon squared. And they coincide. So as epsilon goes to 0, we believe this goes to some universal curve. I emphasize this scaling because this is crucial for conjecturing instability, because numerically you can never go to arbitrarily small epsilon because of computational resources. So this is always an extrapolation. So once you believe that you reached an asymptotic regime. So on the basis of this, we conjectured that ADS 5 is unstable against black hole formation for arbitrarily small gravitational perturbations, in exact analogy to the conjecture we had for the scalar perturbations. Now, to demonstrate this turbulent transfer of energy, we looked at the energy spectrum. Well, energy spectrum, which is the distribution of total energy among the modes, is the key quantity in studying turbulent phenomena. And this is shown here for 3 moments of time. So the red curve corresponds to spectrum of energy for initial data. This is a log-log scale, so this spectrum decays exponentially. Green curve is for some intermediate times, and the blue curve is just a moment before collapse. And you see that this curve exhibits a beautiful power law behavior. With exponent alpha, which is universal in the sense that it does not depend on initial data. It does depend on the model, but it does not depend on the initial data. And this exponent happens to, well, if you fit a straight line to this, you get this number, minus 1.67, which is close to minus 5/3. And, well, to be honest, we don't have analytic understanding of this power law. So in particular, we don't know if this striking coincidence with the Kolmogorov scaling is accidental or not. Okay, so let me summarize. The dynamics of asymptotically ADS spacetimes is an interesting meeting point of several areas of its general relativity, partial differential equations, ADS CFT, and turbulence. And this is pretty much an uncharted territory, and there are fascinating problems waiting for exploration. Maybe I should say that particularly in the PDE community, which is close to what I'm doing, the studies of weak turbulence for nonlinear waves on compact manifolds is an emerging new area of mathematics. For example, quite recently, there was a proof of weak turbulence for nonlinear Schrödinger equation on a 2-dimensional torus. Let me close with some open questions. So, well, I mentioned these two. Maybe I should say this is a very interesting question, which is the role of exact resonances as a driving force for the turbulent cascade. It is not clear what is. This is a very interesting discussion of this problem. But the most interesting question really is what happens outside spherical symmetry. Well, in the spherical symmetric case, which I discussed here, the endpoint of instability is always a Schwarzschild ADS black hole, which is known, actually proved, to be stable. Now, outside spherical symmetry, the natural candidate for end state of instability is the Kerr ADS black hole. But it is not clear at all if this solution is stable itself. The reason is that so-called quasi-normal modes on Kerr ADS in the limit of large angular momentum decay exponentially slowly, which means that, at least heuristically, there should be enough time for the development of instability pretty much the same as in the pure ADS. Well, unfortunately, this problem, as I said, is outside currently available numerical methods if you want very long time simulations. And finally, of course, the question is, what are the implications of all that for ADS CFT? But as I said, I'm not qualified to talk about that, so I'd better stop. Thank you.
There's a question there.
I think one very interesting question here is about ergodicity, and these islands of stability are kind of a violation of ergodicity. What I was wondering is, one thing you might expect is that if you look on very long time scales, like exponential time scales, that maybe there's not really an open set that's an island of stability, but you have something more like a fractal structure in phase space of the ergodic versus non-ergodic regions, something like I understand is expected from dynamical systems. Do you think that's possible, or?
Well, of course, I can't exclude that. So we've been looking at the boundary between these islands of stability. So it's very challenging numerically to really fine-tune to the boundary. So because one should know that these simulations take long. So even though it's 1 + 1 dimensional, they take long because the timescales are very long, and you need to have very good precision not to generate errors at reflections at the boundary. So it could be, well, we believe that, well, as I said, we believe that we reach the asymptotic regime as far as instability is concerned, but I can't exclude the scenario which you mentioned.
There's some numerical evidence for an open stable set on exponential timescale.
No, well, I don't think you can have a numerical evidence that the set is open. So it's I can't imagine that. So,
these stability islands, are there any topological reasons for their existence? And my question is motivated by the question that if one studies quantum corrections, would they disappear or they would be stable?
Oh, well, this is everything is classical here, so.
There is topological reasons for their existence?
No, there is, the topology here is trivial, so it's actually, I think the coexistence of turbulence and time periodicity is not very exceptional, so this is typical. So as I mentioned that if you consider nonlinear waves on some compact manifolds, you usually have these two behaviors, so which coexist. So, and typically, what is, however, surprising here, that these time periodic solutions are stable. So they were constructed numerically, but you can retrace this solution over many, many hundreds of cycles. So which is evidence for their stability. This is surprising.
This Kolmogorov exponent 5/3 that you mentioned, isn't that only valid for, that number is for 3 dimensions coming from the dimension of the velocity field, which is 1/3 in that case?
You're asking if this is...
Yes, you tried to make some remark about the Kolmogorov exponent, right, alpha? 5/3.
Well, so this number is in this model, so this is what we get. Well, in the previous model for the scalar field, this number is different. Okay. And for this, you can study scalar field in various number of dimensions, and if you study scalar field, for example, in the same number of dimensions as here, which is 5, you get an exponent close to 2 - 2. So it's just, well. What does it mean that it's unstable?
What would happen? Does it form a bigger black hole?
Well, I should say that when the black hole forms, well, the horizon forms, then typically there is some energy outside the horizon, and eventually by multiple reflections from the boundary, everything will fall in. So the end state, at least in this spherical symmetric case, is always a black hole which has the same mass as initial data.
Hi. So one more question. Sorry, so are you actually saying, so if I take a non-spherically symmetric perturbation, I turn on quantum mechanics, I just wait and see what happens. Are you actually suggesting that most of the time there's going to be a black hole present? That would be rather surprising entropically. Usually we think the radiation gas should have more entropy than the black hole.
Well, that's the point, that this radiation cannot escape. So yes, that's what I'm
But I mean, it sounds like you're saying there's a huge mismatch between the entropy counting sort of semi-classically and somehow in the long-time behavior of Einstein's equations. Seems suspicious.
Well, that's not...
Can we settle this question by Juan?
Yeah, he's working in the G Newton going to zero limit. So your counting of the semi-classical entropy is always much smaller.
Okay, thank you.
So I guess we can go to lunch now, but thanks.